This conference will now be recorded.
So, very good evening, students. Today, we'll be discussing another important topics on the semiconductor electronics devices chapter. So, here today we'll be discussing about filter circuit. I'll tell you what is that, and Zener diode, and we'll try to learn about optoelectronic devices. So, in the previous class, if you remember, we had discussed about full wave rectifier and a half wave rectifier. So rectification means converting AC signal to DC signal. Suppose this is an AC signal. AC signal has both positive values and negative values, and that will repeat periodically. That is actually AC signal. Now from AC signal we can get DC signal. DC in the sense which has a current or voltage or whatever it is, which does not change its direction. That means it has only positive values. Only positive values. Okay. So that is DC voltage, but DC voltage can also vary with time. Vary in the sense vary in its magnitude. Okay. DC voltage or current can vary with time in its magnitude. Okay. Sometime it can be 1, 0, 5, 10, etc. But it will be always having positive value. That is what we have seen. And see, full wave rectifier means we had used two diodes and we had discussed what are the necessary circuit diagrams that will give you DC signal or positive signal from AC signals or AC input. So this is the black box. This is called black box diagram of rectifier circuit. When you feed AC, you will get DC across this DC voltage across XY. But if you remember properly that in case of half wave rectification, we have got like this, and another half cycle it will be absent, output will be absent, and then again we'll get some output voltage. So this much will be gap or zero voltage. Again we'll get some output voltage like that. It is output voltage of half wave rectifier. Okay, half wave rectifier. Okay, and in case of full wave rectifier, we got output for both the cycles, both positive and negative cycles, when we use two diodes. Okay, so that is what we have seen. But the problem is, you look here, we are getting DC signals or voltage out of AC, but the problem is that the voltage is pulsating. Pulsating in the sense, see, if you look, this is the full wave rectifier output. So this is the pulsating voltage. That means it has its value 0. all the way it increases up to a peak value, then again it decreases to 0, again increases to peak value, decreases, like that. It varies in between 0 to a peak value, maximum value. This is called pulsating voltage, and this, see, this has output frequency twice of the frequency of this input signal. If this has frequency f, then this output voltage will have 2f frequency. Okay, it will have 2f frequency. Okay, but this kind of DC voltage we cannot use in our device or practical application. Okay, we cannot use this kind of pulsating. This is called pulsating output voltage. Pulsating. It is called pulsating output voltage. P-U-L-S-A-T-I-N-G. Pulsating voltage. Therefore, you can understand that this kind of variation, we can say that it has some DC value, DC voltage, plus some AC ripples, AC ripples, AC part. Okay, that is called ripples. Ripple means it always changes its directions or values, etc. Ripples. Okay, so basically the output of a rectifier circuit has DC part as well as AC ripples. These are called ripples. That's why the voltage is pulsating. Okay, it varies, even though the voltage is all the way positive, but it varies from 0 to maximum value to 0 value. So it has AC ripples. So to make this rectifier to make this rectifier output signal useful for our application purpose, we have to make it as a steady one, like this. You look, this is a steady value. If this is a steady value, has a constant value with respect to time, it does not change its value, then it can be used in our practical life. So we have to make this ripple out. If we filter out this ripple, these ripples, then we will have a constant DC voltage. So how to? So this is rectifier output. Rectifier output. I'll clean everything and I'll write. So what we have seen, that rectifier output is equal to DC plus AC ripples. So what we have to do, we have to filter out this AC ripples. We need to filter out this AC ripple, so that we get a constant DC voltage. So this can be done by using a simple circuit that is called filter circuit. As you see here, I have written filter circuit. What is this filter circuit? You can use filter circuit L and R, so some inductor coil in series with this load resistor, or a capacitor you can use. So in this circuit, we have used a capacitor circuit, okay, across this load resistor. You can see that. Okay, we have used this capacitor, a simple capacitor. If you take a capacitor, what will happen? See, I have pulsating voltage, right? So how we get a DC, like a constant value here? See, the capacitor, what capacitor does? Actually, it stores energy, right? Electrical energy. That means it gets charged and discharged. It can be get discharged and charged. Okay. So when the output, this pulsating output is fed to this filter circuit, then see the voltage across this, when the charge, when the capacitor is getting charged, voltage across it will increase. Okay. Voltage across, or in other words, I can say when the voltage of the pulsating output of this filter circuit increases to some peak value, then this capacitor gets stored up to this peak voltage. Capacitor is being chosen in such a way that the peak voltage of this pulsating voltage, peak voltage of this capacitor should be the same as this peak voltage of the rectifier output. Okay. So that is how we can do. And in the next half cycle, look, in the next half cycle, in the first half cycle it goes, see in this ripple, in the first half cycle it goes up to peak value, it is getting stored. In the next half cycle, see the voltage is decreasing. That means this this capacitor will discharge through this RL. Okay, through RL. Capacitor is getting discharged through RL. Okay, so that you get a constant voltage. Okay, so in the next again in the next when the next cycle is starting, see again it is charged. Okay, up to big value. When this voltage, rectifier output voltage decreases, then this capacitor is getting discharged, but the peak value in each case the same. Okay, all cases the peak value of the voltage across, the peak value is same as uh, earlier. Okay, because the capacitor is storing a charge such that the voltage is same as the peak value of the rectifier circuit. Yes, rectifier circuit output voltage. Okay, so this is how we get a constant voltage throughout. Okay, constant DC voltage. Look, this is a real constant, or it is called uh, steady DC voltage. It is called steady DC voltage. TD. Okay, steady DC voltage. So this is how filter circuit can be used. Okay, to get, actually whenever you use diode, junction diode as a rectifier, then there will be associate circuit which is called filter circuit, and from the filter output you get the steady DC voltage. Okay, so this is about filter circuit. Okay, so now so why filter circuit is being used? Filter circuit is being used to filter out the AC ripples which is there in the rectifier output. Okay, all right. Now we go to the Zener diode. So Zener diode is a special diode. Okay, special diode, and it is named after the inventor. Named after the inventor. After inventor. Some I think CV Zener. Okay, I'm not remembering this initial, so let's write Zener. Zener is the inventor of this kind of special diode. So we'll tell you why it is a special diode. First of all, see any diode, it has in the junction diode, it has P side and N side, right? So this is the circuit symbol of a simple diode. Suppose if I give like this, simple diode. But in case of Zener diode, you look, this vertical line is given like a Z. It is written like a Z. Okay, like a Z, alphabet Z. So that is what is the circuit symbol, or yeah, circuit symbol of a Zener diode. Charge carriers. Okay, both holes and electrons. Heavily doped. So this is special made diode or special purpose diode. It has circuit symbol this, and both P and N sides are heavily doped in this case. Okay, so this is what Zener diode is. Now look, we have learned in case of simple diode the IV characteristics we have already read for a simple diode. Suppose in case of forward bias, the current will be like this, and reverse bias, there will be a reverse saturation current, and then there will be breakdown voltage or breakdown. After breakdown, you have current like this. Okay, so I'll just redraw it. This is the simple case I am drawing. In ordinary diode, okay, it is the more or less characteristics. Okay, so the here current is milliampere, here it is microampere range. This is called reverse saturation current because this is independent of voltage, reverse voltage. Okay, so what is the difference between the normal diode and Zener diode? See, anyway, forward bias we are not so much interested to see for the Zener diode, because Zener diode is used to operate in reverse bias. So Zener diode is generally used in reverse bias. Okay, reverse bias, Okay, why? Because look, in this case, in the reverse direction, when the reverse voltage, that means it is here negative. So P side is negative terminal, this is a positive terminal, this is the reverse bias. So when the reverse bias voltage is increased, look, when increasing, the current almost doesn't change, as the similar case in this case also, normal PN junction diode. This is called reverse saturation current. Reverse saturation current, suppose reverse saturation current. Now if you increase, if you go on increasing this reverse bias voltage, there will be certain voltage that is called breakdown voltage, that is called Zener breakdown voltage, at that Zener breakdown voltage, that is Vz, Zener breakdown voltage, there is a voltage for a Zener diode. Basically this is the breakdown voltage for Zener diode, that is called Zener breakdown voltage, or sometime it is called Zener voltage. Okay, let us say Zener breakdown voltage. Voltage of the Zener diode, there will be a very huge change in the current, whereas there will be very least or almost no change in the voltage. Look, I will show you this in this figure. Let me just draw a little bit here. I'll just draw the reverse part. See, so this, suppose this is VZ, general breakdown voltage. So the current increases very sharply. Even if you increase the voltage or decrease the voltage near about this general breakdown voltage change in the voltage does not occur, almost does not occur. In the sense, suppose you have general breakdown voltage some 6 volt. I am just supposing. Okay, if you increase this general breakdown voltage from 6 to some 6.05, you will see a huge change in the current. Okay, even now if you change this current to little bit more, like voltage, if you change the voltage little bit more, suppose 6.1, then you see, if suppose the current was here some 100 microampere, here maybe just by increasing 0.5 volt general breakdown voltage, after general breakdown voltage, if you increase it very little, then the change will be almost 100%. See, maybe you will get 200 microampere current. I mean to say that at this, like when a Zener diode is operated in reverse bias condition, at its Zener breakdown voltage, there is no change in the voltage. If you increase or change the voltage a very little, okay, then also you see a very huge change in the current. Okay, very huge change in the current. Very huge change in the current. Suppose I have given example here. So if you increase voltage by 0.05 volt, then also see the current is changing to like 200 microampere, 100 to 200 microampere, almost double it becomes. Okay, or maybe not only double, it becomes maybe more, much more than that, 5 times, 10 times it becomes. Okay, current becomes 10 times, 12 times, something like that. Okay, or sometime, yeah. So this is a special property of Zener diode. See, what is the difference? In normal case, the diode goes like, see, reverse bias current goes like this, and there is a change like this. Okay, you look, this is a continuous change in case of normal diode. If you increase the voltage even after breakdown, then slowly the current increases in a rapid, a rapid manner, or rapidly. After increasing voltage, it will increase the current, but change in the current will be obviously much more than earlier. But in case of Zener diode, you look here, almost voltage is not changing. Here, at least normal cases, voltage changes up to here, like this. This much change is there. But see, Zener voltage is almost constant, but the current is changing like anything. Okay, look, I'll clean everything and show you here. See, this is a very sharp change. It is changed like this. So voltage here, Zener, see, voltage is almost not changing, but the current change is there. See, suppose here it was 10 microampere, here it becomes some 50 microampere. Okay, 50 microampere, here it becomes 500 microampere, but voltage change is very least, or almost no change in the voltage. So this is a very special property of Zener diode, and this property is being used. So this property of Zener diode, which property? That voltage does not change, but there is a huge change in the current. So this property of Zener diode is used to make voltage regulator or stabilizer. Regulator or stabilizer. You must be very much familiar with this word stabilizer. Okay, stabilizer. Stabilizer, what does it do? Suppose there is a fluctuation in the voltage, then you don't feel the fluctuation. It adjusts. See, in this case, Zener diode is being used. Even if you increase or decrease the voltage, that change is not being felt because Zener diode voltage does not change. Even if there is a change, huge change in the current, but Zener voltage does not change. That's why when you use a Zener diode in reverse bias in a voltage regulator device, then if there is a fluctuation in the input AC signal, then there will be fluctuations in the, see, if you have AC mains, you connect it to rectifier circuit to make it DC. Okay, rectifier circuit. Then output you take this output through a capacitor filter circuit. Okay, filter circuit, and then get the output. Okay, as I had shown in the previous figure. Look here maybe. So see, when the AC is fluctuating, so when AC is fluctuating, AC input, then the output here also fluctuates. Okay, fluctuates. Okay, so if this output voltage is fluctuating, then there will be a problem in our device application. So to make it stabilized, so what we can use is, we can use a Zener diode in reverse bias condition such that there will be a change in the current, but there will be no change in the voltage, and that particular voltage we will be using as, so if we use Zener breakdown voltage as our working voltage, since that does not change, Zener breakdown voltage, okay, Zener voltage or the voltage across the Zener diode does not change. If we use that voltage as our output, like input in some devices, then that voltage will be always stabilized or regulated voltage. That is called voltage regulated device. So you look here, Zener diode, how to use Zener diode as a voltage regulator. This is the required diagram circuit diagram of a voltage regulator. Suppose voltage regulator, so where Zener diode is being used. See, in this case, the unregulated, that means fluctuating output of a filter circuit is fed to this circuit. This circuit constitute, like it consists of Zener diode and a series resistor with Zener diode. A series resistor with Zener diode. So RS is connected in series with Zener diode. So one part, like say one end of this resistor is connected to the unregulated supply, DC supply, unregulated DC supply. Okay, here. Then a Zener diode is connected to this unregulated voltage supply along with a series resistor RS. And see what we do, we always take the voltage across the Zener diode as our working input voltage. Working input voltage in any device. Try to understand this. This is a voltage regulator circuit diagram where look, this unregulated supply voltage is fed to this particular circuit. One Zener diode, and with Zener diode there should be a series resistor. Okay, this series resistor you have to choose according to certain properties, like how much Zener voltage, Zener breakdown voltage is there, and how much output you need, and how much input is there. According to that, how much unregulated voltage is there, how much output you need to get across this Zener voltage, Zener diode. So accordingly, you have to choose the Zener diode. If you need some 12 volt regulated voltage, then you should use a Zener diode which has breakdown near around this 12 volt. Okay, at least 12 volt. Okay, that is the thing. So at this condition, there will be no change in this voltage. See, in this series circuit, among see the voltage across this Zener diode itself is used as working input voltage in case of device. Generally, when you go for BSc laboratory or practical sessions, they will ask you to, like, your teacher may ask sometime to make a regulated power supply. So in that case, the use of Zener diode you have to do. Okay, so let us understand this, what happens. So suppose changing means what? Unregulated supply means what? Suppose your voltage, this voltage, it varies from 10 volt to 15 volt. Okay, this much it varies. Your unregulated supply voltage varies from 10 volt to 15 volt. Okay, but your input should be some 12 volt. Suppose input should be some, your regulated voltage should be some 12 volt. So you have to choose a Zener diode such that it has a breakdown voltage around 12 volt. Okay, so in this case, when the voltage changes, suppose it is increased, or it is going from 10 to 15. When it increases, see what happens, the current voltage, if the voltage across this increases, the current through this also will increase. Okay, current Is suppose. Okay, and current Iz here through the diode, Zener diode Iz. So current, see, since they are in series circuit, the current, if the current increases through Rs, obviously current will increase in this also. Okay, in the diode also, Zener diode also. Okay, but in this case, you look, whenever the current is increased, the ISRS, this value goes on increasing. That goes on increasing. Whereas the voltage across Zener diode doesn't increase. Okay, it does not increase because it is working under reverse bias condition, and at reverse bias condition, Zener breakdown voltage does not change. Okay, so that's why you will see the voltage across this RS will increase as the current increases, but voltage across this Zener diode does not change even though increase in current occurs. The current is increasing but voltage does not increase. Okay, So this is actually the action of diode in the voltage regulator circuit. Now we'll just try to solve a numerical problem. I'll give you uh, some values. Okay, let me just draw the same circuit. Okay, so suppose this is 250 ohm, 250 ohm series resistor. This RS, this is RS actually, and if the Zener diode is connected here. Okay, Zener diode is connected in series with this, and other part is here. Okay, this is the, see, suppose the Zener diode having breakdown voltage 15 volt. So VZ, this breakdown volt, this has breakdown voltage VZ as 15 volt. Okay, and see this unregulated voltage, it has 20 volt unregulated voltage. Okay, now the load voltage is 1 kilo ohm. Load voltage is 1 kilo ohm. Kilo ohm. Okay. So in this circuit, you have to find out the current through the Zener diode. You have to find out the current through the Zener diode. Okay. So how to find out the current through Zener diode? You have to find out the current through Zener diode. So what is the current through Zener diode? This is the question. Deepa, would you like to try? Would you like to try, Deepa? See, diode is a non-linear device. Even if we know that the voltage drop across the diode is 15 volt, because it is VZ, it does not change. VZ does not change. 15 volt. Okay, 15 volt. And this has 250 volt. See, the voltage is given. So this is 20, unregulated voltage 20 volt. This is 250 volt. If you see, if you have some current is through this way, okay, the same current will flow through the Zener diode, right? Ideally, isn't it? Similar current. Okay, anyway, let us do the problem. So first of all, this is is, okay. uh See, this is a parallel circuit, right? Parallel circuit. So if the current is flowing through is, see, with this rs, then there will be two currents flowing. One is along z, okay, through the z, it is iz, and another current through this. Okay, that means this current iz is not equal to is. Okay, that is what is the idea. Anyway, so look here, we know up to here what is the voltage drop. Voltage drop across this is 15. So what is the voltage drop across this? Rs. So voltage drop across Rs, suppose that is Vs or Vr. Let us write that is Vrs. Vrs will be 20 volt minus 15 volt. Okay, this is the voltage drop across this resistor. Okay, now you know the resistance, you know the voltage drop across this, so you will get easily what is is. Okay, is means the current through the resistor RS. So let us find out. This implies that IS will be VRS by RS. Okay. So VRS we have got 5 volt divided by 250. Okay. 250 ohm. This will give you 1 over 50 ampere. So it is, if you multiply here with 1000, then you get around 20 milliampere current. Okay, 20 milliampere current. Okay, across through RS. So you are getting 20 milliampere through this. Now the voltage drop across this is Vz. Okay, Vz. So the same voltage will be across this resistor also, right? This resistor also. Okay. So what we can do, we can get the current what is flowing through this load resistance RL. Okay. We know the voltage across this load also will be equal to Vz. Okay. So IL. So what we have got so far? Look, we have got. I'll clean this portion. We have got the current through the RS, through RS. We have got the current IS through RS, that is this current, as 20 milliampere. Okay, and see, we know the VL voltage across this load resistor will be Vz. Okay, if we want to get the current through the load resistor, that is IL is equal to VL by RL. So this is RL is 1 kilo ohm. This is Vz. Actually, VL means Vz. RL means what? RL means 1 kilo ohm. Vz is 15 volt divided by 1 kilo ohm means 10 to the power 3. Okay, so you get 15 milliampere current. Okay, so you got total current in the circuit like through RS is 20 milliampere, and this current upon coming up to here, it will be branched into two. One will be through Z, through the Zener diode. Another part will pass through the load resistance. Okay, so look, the remaining current, so 20 ampere milliampere minus 15 milliampere would give you the Zener current. If you just take the difference, the current through the Zener diode will be 5 milliampere. Deepa, is it clear to you? Is it clear to you? See, the current which is passing through RS is the sum of the current through the load resistance plus through the Zener diode, that is IZ. So you have to remember IZ plus IL will be equal to IS. Since this load resistance is in parallel with the Zener diode, it is because of that. If the load resistance is not there, then IZ will be IS, equal to IS. Okay. So in this case, what is the current through the Zener diode? That is 5 milliampere. So that is the current through Zener diode. Okay. I hope you have understood this problem. Now we'll start with a little bit optoelectronic device. So today what we have learned? We have learned what is filter circuit, how it works, and why do we need filter circuit at all. Then we have learned what is Zener diode and what is its special property. Zener diode is actually Zener diode works in reverse bias condition. Reverse bias. Why reverse bias? We will discuss now. So it works in reverse bias condition because the near the breakdown voltage, there is no change, almost no change in the voltage, but there is a huge change in the current. So that property is being used to make a voltage regulator, okay, or a stabilizer. So why this? See, there is almost no change in the voltage, but why then there is a huge change in the current? Why doesn't it happen in case of normal diode? First of all, P and N both are heavily doped. Heavily doped. That means it has large number of holes and electrons as charge carrier. At the same time, you have huge number of host atoms. Host atoms. Huge number of host atoms or the ions. Host atoms or the ions. Okay, host atoms or ions are there, huge in number because it is heavily doped. Anyway, so look, we know depletion layer is created. Suppose this is P side, this is N side. So there are negative acceptor ions over here, and here there will be positive donor ions. Okay, sitting over here. Now already there is a built-in potential that is called barrier potential. Okay, we had written that time. This is V I, or you can write simply V0. This is a barrier potential. Sometimes it is written as VB also. Let me write it as barrier potential. Okay, or built-in potential, that is VB across the junction because of this depletion layer. And see this layer, because see when you make a very heavily doped PN junction, the thickness of this depletion layer will be much less than 10 to the power minus 6 meter. Okay, it will be much less than this thickness. And suppose you have applied a potential V across a very thin region, very thin region. So suppose it is 10 to the power minus 6 meter. See the electric field, it becomes very large, of the order of 10 to the power 6. This is actually breakdown voltage or ionization voltage of air molecules or etc. So this voltage, this electric field, this much electric field, this is actually very high electric field. Okay, Newton per, or here volt per meter. It is a very huge electric field across the depletion layer. When when P and N sides are heavily doped, the junction will have very less thickness, and hence already the electric field across the junction will be very large. Okay, of the order of 10 to the power 6 volt per meter. Okay, of the order of 10 to the power 6 volt per meter, the electric field across the depletion layer. So electric field will be of the order of 10 to the power 6 volt per meter, and it is a very huge voltage. At this voltage, what happens? This are suppose host atoms, or at the depletion layer as well as in the P region or maybe in the N region, there are host atoms. These atoms has again their electrons in the various cells. Okay, at least the valence electron of these host atoms also will be coming out, and it will give rise to the conduction process. It will take part in conduction process. See what happens, the electric field, if the electric field is so high, when we apply a breakdown voltage, at this voltage, the because it is reverse bias voltage, the electric field increases again higher and higher. At this high electric field, what happens? The host atoms become ionized. Ionized means what? The valence electrons comes out because of this very high electric field. And these electrons, as soon as it comes out at the near the depletion layer, there is a huge electric field which is positive here and negative here. So the electrons will be from, if the electrons are produced or atoms are ionized near the p sides, then electrons will be actually dragged or pull out towards the n region. Okay, and that's how the carrier number of carriers flowing will be increasing, and because of that there is a huge change in the current after Zener breakdown voltage. Okay, even if you increase a very less amount of voltage, or maybe voltage will not change at all, but the current may change or very in large amount. It will vary in large amount. Okay, so this is about Zener diode and how like Zener current increases so much because of ionization or rupture. It is called rupture of the atoms. Okay, atoms has this host atoms have their electrons again in the core electrons. Okay, the electrons even from the relatively core cells also, electrons will be pulled out by such a high potent like electric field across this depletion layer. And so I have discussed why the electric field is becoming so large, because p and n regions are heavily doped, and hence the thickness of the depletion layer will be very thin because of that. And also you are applying reverse voltage to the Zener diode, so that also will increase this barrier potential. Okay, or this built-in potential which will ionize the host atoms. Okay, and those electrons will be actually pulled out towards the n side, and that's how you get a huge current. Okay, in case of Zener diode. Okay, so this is about Zener diode and its application, etc. So I'll just quickly discuss about optoelectronic devices little bit, and then we'll stop today's class. See, so optoelectronics means, see, optoelectronics. So you can see two words, opto plus electronics. Okay, that means there are certain kinds of diodes. Okay, so diodes actually, in diode, how diode conducts, or what are the basic principle of operation. You need to produce somehow electrons and hole pairs as charge carriers. Okay, to conduct, for diode to conduct, and these electrons and holes are made to flow. That is the basic principle in p-n junction diode. Now, in p-n junction diode, you have, if you remember, you have conduction band. Okay, conduction band, right? EC, and then you have valence band. Okay, so valence band, sorry, this is suppose conduction band. Okay, EC, and here it has energy level EB, conduction band EV, sorry, EV valence band. Okay, so you have valence band, this is valence band, and this is the conduction band. This is the lowest level of the conduction band. So, and in between valence band and conduction band you have a band gap. You have a band gap. So in general, in case of diode, if you want to get current, you should have electrons in the electron population has to be increased in the conduction band, so that you get current. Okay, so but there is a gap, how electrons, generally electrons at room temperature and all, electrons will be there like highly populated in the valence band. Okay, they will be highly populated in the valence band, but there will be very rare population in the conduction band. Now if you want to get some current through the current, then you have to populate this conduction band by taking some electrons from valence band to conduction band. Okay, all right. So this is somewhat you can understand that creation of charge carriers, holes and electrons. This is creation of holes and electron pair. Okay, at the junction, at the PN junction, see at the depletion layer, near the depletion layer, or at the junction, suppose this is P, this is N, at the junction, if you make a device with this PN junction diode, suppose you have a transparent window, okay, transparent window at the junction, transparent window, transparent window, then you can shine with light photon to this junction, right? So optoelectronic device means when you shine a diode with light, but you get electrical signal. Okay, that means optical energy is getting converted into electrical energy. So that is optoelectronics. When you use light as input to the diode and get some current. Okay, so when you shine a diode with light and get some current, that is called, actually there are three types of optoelectronics. There is a photodiode, photodiode, photodiode. Actually, this one, when you shine the PN junction with suitable energy of like shine with photons or light of suitable energy, then photodiode, what it will do? It will actually, it will create some electron hole pairs, and they will conduct so that you get some current through this junction. Okay, some current you will get, and this is how you can actually detect optical signal with the photodiode. So you can use as detector, photo detector, used as photo detector, photo detector. So photodiodes are used as photo detector, and then there will be light emitting diode or LED. LED, light emitting diode. That means a diode can emit light. Okay, so that, see, all the phenomena here in the optoelectronic devices involve this generation of charges and movement or the flow of charges, charge carriers. We will discuss these things in detail in the next class. Another optoelectronic device is actually solar cells, okay, or photovoltaic devices, when the photon or the light is directly converted to electrical energy, solar cell, okay, or photovoltaic device, photovoltaic applications are there. Photovoltaic, okay. So diodes are like used to make certain optoelectronic devices. That means in case of photodiode, if you shine the diode with light, it will give some current. So that will help you to detect some optical signals. Then you have LED. If you give some electrical biasing here in the LED, okay, then that junction diode will emit some light, okay, that is called LED. Okay, that is called LED, light emitting diode. If you give certain electric biasing to the diode, it will emit light. We'll discuss all these optoelectronic devices in detail in the next class. So, Deepa, you had joined the class in late. We had already started in started the class at 5:30 today. So I'll stop it here for today. If you have any doubt, you can ask me now. If you have some quick doubts, otherwise we'll stop the class here. Next day we'll discuss optoelectronic devices like photodiode, what are the working principles and how it works, then LED, how LED works, solar cell, how solar cell works. All those things we will discuss in the next class. Okay, Deepa, so do you have any doubt, any quick doubt? Okay, if you don't have anything, I'll stop it here for today. Okay, so bye for today. We'll meet again on Wednesday, and on that class, like in that class, we'll discuss optoelectronic devices. Okay, so thank you for today.